Good afternoon, everyone. Thanks for your time, and thanks, Professor Fu, again for the content you're going to deliver today. I might just start off with a little bit of housekeeping. Use the Q&A. Feel free to send through any questions or feedback or anything from round one that you just want to let us know about now. We'll be happy to answer any questions on that. What I'll do is I'll just give you a bit of an update on where we're at with finalising round one, and then kind of what's happening for round two. So as far as round one goes, firstly, thanks for all your support to get that up and running. I know there was some potential challenges at your schools with the tech side of things, but from what we can see, that everyone's up and running and everyone's submitting now. Off the back of that, we did send an email out to a select few schools late last week, just giving them an extension until Thursday, just because it took about a week or so for them to get up and running. So we've just given them those extra few days. And then there was some schools in Queensland that have been affected by the cyclone, either power outs or whatnot. So we've also given them till tomorrow to submit their answers. So how that works is, look, we take all the answers out of the LMS. We're checking them manually just to make sure that they're correct, and then we're going to average the scores. We'll look at publishing all the scores probably, I would say, Tuesday at the very latest, Wednesday next week, just to allow us time to make sure they're correct and do some sense checking on those. The reason we're smack bang in the middle of getting round two content finalised, getting all that built in the LMS and having that ready to launch on Monday. So how round two will work is we'll release the LMS and round two content Monday morning, and then students should have access to the VM by that afternoon. So they'll give them plenty of time to go through the theory-ish units with the chance to access that VM later in the day. Now, just to kind of flag how that looks, there won't be as many theory units as round one. Round one was all around that foundations and giving them the basics. Round two is a lot more technical, and it's a lot more located in the VM. So there's not as many theory units to go through, but we do give a baseline theory on some of these technical concepts because they're probably things students haven't worked on before. Again, Q&A, if you've got questions throughout the webinar, please let us know. Happy to answer those. But really what we're going to do today is it's all for Professor Ernest Fu. He will be talking about network packet analysis, which I think is going to be quite interesting. This will be one of the key technical elements of round two. And then, Ernest, what are the other technical elements we'll cover in round two?
So we're looking at logs, so system logs, and we're also looking at web security. So next week, gosh, it'll be next Wednesday. That will roll out pretty quickly. Yeah. Next week we'll concentrate more on web security type things, and give a bit of background to that in terms of what you can tell the students and what kind of tools that we kind of expecting you guys to use. And I think that's one of the other things is that, the tools that we present, the tools that we install on the system, I mean, there's more than those. There's a lot more that can be used. These are just the ones that we introduce. And we also hope that we'll be able to be, easy to use in terms of accomplishing the goals that we need. So yeah. Did you want me to start?
Yeah, go for it. All about you today. It's all about you today.
I thought that there was something else that you were going to say.
No, I'll touch on kind of how round two will wrap up at the end. But no, over to you with the technical stuff. That's great.
Okay, cool. All right. So one of the things that so one of the three aspects of round two is all about networks and network packets. So just to start you guys off, for those people who haven't got an IT background, and like this is the thing, some people who do have an IT background, they'll probably know a lot of this stuff already. But there are some of you out there who've never really touched this before. So I'll give you a bit of basics on networking theory. And so the thing with networks is that, or more than just networks, this is like data communication. So communicating, across the network, right? So it's all about layers, right? Because it's really a complex system to be able to send a message from your desk to somewhere totally over the other side of the world, and then a message from them back again. Right? And it all happens in the blink of an eye at the speed of light as the data gets transmitted across the copper wires or the fiber cables or over the air even. That communication happens. So it's pretty complicated. So the way they simplify things is to think about network communication as a model and to split that up into layers, right? So there are multiple layers that the message that you send has to go through. Okay, and the weird thing is that these layers are largely theoretical, right? So and I will talk about what's known as the OSI model. And the OSI model has 7 layers in which a message goes through before it gets transmitted out onto the wire. Right, and then when it's received, it comes back up through all of those 7 layers before you even see it on the screen. Right, so yeah. But the ironic thing is that we teach this all the time in classes, and even if you do a Cisco class or something like that, which is all networking based, they'll teach this. But the reality is that this particular model isn't implemented exactly. So it's very theoretical. It's not actually implemented exactly like the way we present it. So I will point out some of the layers which are much more realistic. So the 7 layers. So it starts off closest to the user, the application layer. The presentation layer is next, then the session layer, the transport layer, the network layer, then the data link layer, and the physical layer. So starting at the top, the application layer is something that we all see, right? So whenever we start off a program, it's an app, right? We start the app, it's at the application layer. Okay. So most often in the example that I'll go through, it's like a web browser. So the web browser is the application that we start, right? And then usually the application is where humans, us, interact with the network system. So you might click a link, or you might type a URL in and then hit enter. And then once you actually hit enter or click the link, you're actually sending a message out over the network, right? So the application layer sends something down to the presentation layer, and that's where the format of the data gets sorted out. Then after the presentation layer, it goes down to a session, and where theoretically a session would set itself up. So a session is a group of messages within a session, right? But the thing is, the application layer is real. The presentation and session layer tends not to be used so much. They all get incorporated up into the application layer, right? So even though we teach it and we talk about it, but in reality, it's not actually implemented. However, at the transport layer, this is where we actually set up a protocol between the sender and the receiver, right? To say, basically at the transport layer, it's saying, what application is generating or should receive a particular packet. Okay. So what application, what program on the computer? The next layer down is the network layer, and that's basically saying, well, what machine should get this message, right? So what kind of like address? So inside networking, we have things called addresses, and there's actually addresses at each of these different layers. Okay, so at the network layer, most people would have heard, maybe if you've ever dabbled with network communications before, something called an IP address, right? So an IP address is like usually 4 numbers separated by a dot. And those numbers don't go up beyond 255. So, an IP address could be 10.10.10.10.1 or something like that. 4 numbers altogether. So an IP address. The great thing about the IP addresses is that theoretically, again, is that each machine that's connected to the network is supposed to have a unique IP address. So this is one way of being able to send a message from machine to machine, right? And this is machine all the way across the world. Okay? Now, that's the theory, but as the internet grew, we actually ran out of these numbers, so we had to try to find new addressing systems and other kinds of things. But just for simplification, at the transport layer, it's the end-to-end communications. It's like, we're going to send a letter to this particular address, and we need to know where that address is, and we fill in the details and it's sent all the way across. Okay. Next layer down, so that's the network layer. Next layer down is the data link layer. At the data link layer, we're talking about addressing in terms of what's the next hop, right? What's the next place to send the message to? So the difference between the network layer and the data link layer is that the network layer, it's end-to-end, but the data link layer is all about, yeah, that's great. I've got to get this to Washington, D.C. or wherever, but I need to know where to send the message right now, kind of thing. And so it's like, which computer along the way? Because what happens in a computer network or data communications is that, there's no direct link from your machine to the destination in Washington or wherever you're trying to send things to. Your message gets passed from one machine to another device or another machine, and then it gets passed to another machine, and then it's passed to another machine. Right? Now, all the machines aren't PCs or laptops like you have, but they're special network devices, routers and switches, that will pass the message on to each other until it finally gets to the destination machine, which will probably be a server somewhere. Right? So anyway, the data link layer is the one that works out, well, in passing this message, this package from one person to the other, who's the next person in line that should get it, right? And so the data link layer works that out. So it has its own addressing at that level as well, and it's called a MAC address, right? And yeah, so each of these have different formats and other kinds of things. The final layer is the actual physical layer. So the physical layer will be different depending on the type of network that you've got. And the data actually gets represented differently depending on what that is. So it might be particular frequencies if you're on wireless, or it might be different voltage levels if you're on a wired connection, or different light frequencies and other things if you're going over fiber optics kind of thing. So the physical layer is the actual representation of the ones and zeros that gets sent out across the network. So it is I guess it is kind of complicated with these models. The message that you're sending, like, can I please have this webpage, has to go down through each of these different layers. As it goes from application, goes down to transport, it says, oh, this message has to go to this other program at the other side there, like the destination program. They work out what the destination program is. Right? And the way they work that out is through an addressing system again. And I forgot to talk about the transport layer addressing system. The transport layer addressing system is your port number. Okay? And port numbers are kind of like, between 1 and 65,000 or whatever. And because pretty much they guess, oh, you won't get 65,000 programs running on a particular computer at one time. I mean, nowadays you can, but back then you couldn't. And most of the time you don't really want that nowadays. Anyway, the port number is the number that's associated with the program running at the other end where you're going to send something to. Of course, the sending end also has a port number as well, because what happens if the other end wants to send a message back, right? How's it going to get the message back into which program? So there's a matching port number on both sides. Same with the network layer. When I'm talking about IP addresses, there's a destination and a source IP address so that we can talk back and forward, right? So if we did send the message to Washington DC, then that message, they know what the IP address is if they want to send a response back, right? So, and then but the data link layer doesn't necessarily, mainly because it's just the next step, right? It's just got to work out where's the next step that you have to send things to, and that's always going to be usually the same, because everybody that's connected usually has a single way out of your networks, right? And if you're sitting at home, like I'm sitting at home, you will have a modem or a modem router, and that is your one way out of your home network, out into the big wide world. And that's usually what happens on your corporate networks as well. You'll split up into different subnetworks, and then each of those subnetworks will have one gateway out, right? And usually that's what happens at the data link layer. So and work out, well, do I need to send a message locally, like to the machine sitting next to me? If I don't, then I need to send it to that big gateway, and then hopefully it'll get sent out to where we need it to go. So, so that's a data link layer, and it has a MAC address, and then of course the physical layer again, 1 to 0. So, so I think we can move. I think I've talked more about this slide, and I should have gone to the next slide. Ross, so can we go to the next slide? Yes. So one of the cool things about networking is that, you know how I was talking about the 7 layers, and you can see there's a sender layer and there's a receiver layer. And you can see here in this diagram, we've got rid of presentation and session. And we've got like mostly the real ones that are implemented. And it's not to say presentation and session layers don't exist, but they just get subsumed by application. Everything happens inside the application, because the application usually deals with presenting it to people and stuff like that. So anyway, it's all inside there. But the key part is that when you send a message, right, it's at the application layer at the source, right? You create the message by clicking the link, and your application says, this is a message that says Ernest wants the Google webpage. Okay, so that request gets sent down to the transport layer, where what's known as encapsulation happens, because when that message goes down, a header and a footer gets slapped on it, right? And that header and the footer has the IP, the port number for the other end, right? Goes from a transport layer to the network layer, header and a footer gets slapped on again, and over the top of the transport layer header and footer. So the message actually grows a little bit bigger, right? But in that additional things that get added on there, the IP address. So my source IP address and the destination IP address for the message get attached to this packet, right? As it moves down, then we go to the link layer, and then again, header and footer gets slapped on it again. And then inside there, it's saying, well, okay, you've started, this is your MAC address. Where is the next link MAC address? We'll hook it on there. And then all of a sudden, when we get to the physical layer, we've got a frame now, which has like all the information that particular message needs to get to the other end. It gets sent out across the physical network, but all of that information is in there with it. As it goes along, each of the layers will kind of like get looked at, right? The link layer will get looked at, the network layer will get looked at, the transport layer, and then the application layer as well. So when you get received at the other end, right, each of those layers, you'll get that big packet at the other end, goes up to the link layer, they'll check out the link layer MAC addresses and say, have I got to the right place? Yes. All right, let's get rid of that layer. Shrink it a little bit more. Up to the network layer. Is this the right IP address? Yes. Shrink it a bit more. Up to the transport layer. Is this the program that needs it? Is it the web server that I'm looking for, the Google web page server with the search screen? Yes, it is. Okay, so we don't need that anymore. Bang. Shrinks again, and then goes to the application layer. And then at the application layer, it gets my search string. And goes, Ernest wants to search for llamas or something. And then, and then the application can run its thing. Right? But this is all this encapsulation, basically adding the headers and footers, happens whenever you send and whenever you receive a message all the way through. Okay. So you can see each of the times whenever you send, I've got the thing down there, there's a port, there's a source address, a source port, a destination address, and then, the actual application that needs it. All right, next slide. All right, so you thought that was confusing. Hopefully it's a little bit clearer. But each of those layers has a protocol, okay? And the protocol, so in networking, right? A protocol in general is a specific sequence, a specific way of doing things. So we have a social protocol. Whenever I see somebody, I go, "Hi, how are you?" And then usually the person, no matter how they feel, go, "Hi, I'm fine. I feel great." Something like that, So there's a protocol. A message gets sent one way, "Hi, how are you?" And an expected message, "I'm fine," gets sent back the other way, right? And then a conversation happens. And usually the conversation could be one person talking, the next person talking, one person talking, the next person talking. That is a protocol. And in actual fact, in the data communications, protocols happen at each of the layers. One of the most important protocols that we use is the hypertext transfer protocol. And this protocol actually happens at the application layer. And in actual fact, some of the more complex protocols happen at the application layer, right? Because each one of those ones at the application layer is generic for a particular application that we're using for. So in this case here, HTTP is used for web applications. Okay. The other protocols that are used, like there's tens of them. I was going to say hundreds, but maybe not so many hundreds. But there's a lot of them, but they happen at each of the different layers. Once you get past the application layer, which is very specific, when you go down to transport, it then becomes quite generic. And there's only really two different main types. One's a TCP and one's UDP. At the transport layer, those protocols are just about the way that particular layer behaves. So TCP behaves a bit like a telephone call, where there's actually a session in place. When you make a telephone call, you talk to that one person and you talk back and forward across that channel. So that's how TCP works, right? Whereas UDP, also at the transport layer, when you talk about things, it's only a single message. It just sends a single message out, single shot, and then that's it, right? There's no continuous back and forward and tracking it. So there's two different ways of setting it up, and they're used for different things. So TCP is used for transmitting large amounts of data all in one place. So if you're going to upload or download a file, you'll use TCP, right? But it takes a lot of setup and tear down whenever you make a connection, right? But for UDP, it's a one-off, right? And so we tend to use UDP for one-off streaming protocols. So whenever you're streaming a video or something like that, it's usually UDP. Because you don't have to set something up, but you have to send a message in real time, or the video picture or whatever in real time, so that it displays properly. The movements all work. There's no jerkiness or anything like that, or blurriness. So yeah, we tend to transmit video and sound using UDP. The other thing is that a lot of the things that happen with TCP is all about making sure we don't lose any data. However, when we're transmitting or broadcasting sound and video, if we lose a frame somewhere, it doesn't really matter. Or if Ernest's hand is a little bit blurry on the fingers, it doesn't really matter so much, right? So if you're streaming stuff, if you lose information, it doesn't matter, right? So it's more about the speed. So that's TCP. At the network layer, there's only one protocol called IP. And yeah, so those are examples of different protocols at different layers. However, where was I? I was talking about the application layer protocol, and we'll talk more about HTTP next week when we talk about web security. But just to get you a bit of a head start on that, to tell you a bit about the HTTP protocol. It actually only has two main messages. It's a very simple protocol. And you've got to remember, HTTP has grown up before our eyes. Because remember, originally HTTP was just used to access academic text. And that was mainly words, and maybe you might get the odd picture. Okay, and I don't know if people have been around long enough, like I have, but that's what it was back in the day, right? And nowadays it's just used for everything. It's even used for this, video conferencing and other kinds of stuff. So yeah, but in the beginning, in the end, and if you boil it right down, there's two messages: a get protocol and a request protocol, and a request message and a response message. Right? The request message is, can you please give me this web page or this resource? Like it could be, give me this picture kind of thing, right? And so what happens is the browser sends that message off to what's known as a web server at the other end, right? And the web server will say, oh yeah, you're asking for the Google logo. All right, we'll go grab the file that contains the Google logo, and we'll respond. We'll send it back. Right? We'll serve it back to the other end. Right? A bit like tennis, serve and the response. Anyway, so it sends it back, and then so the response message in response to the request goes back to the other end. And in the old days, that was all that we really needed, right? But the protocol itself is missing some things. The original protocol didn't really remember each request. Each request was new to it. It had really short memory. Every time you sent a request, it didn't remember that you previously had sent another request before. Okay. And so in the very first types of HTTP web pages, it would never remember your name. Right? You'd have to think about different ways for the server to remember your name and to give you a customized web page back. Because what would happen is it would just post just the standard web page back. And it would have nothing like what we have with social media now, where you have an account and it remembers, oh, it's Ernest, and here are all Ernest posts, and all of these kind of things. None of that happened. So they had to build the protocol to do that. Let's go to the next page. Right. So they built an additional feature to the protocol, and that was what's known as cookies. Right? So you might have heard about cookies a long way, especially nowadays when you go to websites and it asks you, do you want all the cookies, or do you want some of the cookies, or things like that? And a lot of people will kind of go, cookies? I have no idea. I'll just go yes, right? But basically what cookies are is a mechanism that built atop of the original HTTP protocol as a way for a browser to remember to tell the server, I've been here before. And my name is Ernest, right? So then the server would then go, oh, it's Ernest. All right, Ernest has a special page. Let me get all the special stuff for Ernest, put it on the page and send it back to him. So then I would get customized messages in terms of I would be able to see in the top corner that Ernest has logged in. Okay. And so previously, the server with HTTP would not remember that Ernest had previously logged in. So this is how cookies work. First time I log in, there's no cookie, so I just send a normal request, goes to the server. The server actually sets a cookie in the response, and basically it says in the response, hey, Ernest browser, I want you to remember that you've seen me before, you've come to me before. Like it's kind of sad because the server is kind of like, an old person who forgets all the things. So, because that's how they're built, right? They're built to just send stuff back, and they don't remember. They're not supposed to remember. So what happens is it actually sends a message within the response to say, if you ever come back to me again, send this to me, and I'll remember who you are. I don't know. Like there could be a plot for a romance novel or something like that. I'm pretty sure. I lose my memory all the time, but if the next time you see me, send this special message. And this is basically what happens with the cookie, right? First time it goes through, server sets a cookie and says, if you ever come back, give me this secret number or this unique value, and then I'll remember who you are. So then the browser, then whenever it goes back to the same server, will send the cookie information, and then the server goes, it's you. All right, let me give you the information for you. Right? And then that's the way the server just remembers stuff. Right? Now, in terms of security, cookies then became really important because cookies started holding credentials, right? Cookies would start having a token that says, you've authenticated as Ernest before. So when I go back here, you can show Ernest all the important stuff like his bank balance or his tax files information or his insurance information or whatever, right? Because he's been here before. The other way that cookies are used is for servers to actually track where you've been, right? So, if there's a Facebook web page or other kinds of things, the cookies can keep a track of where you've been and sends that information to the server to say things. So that's why nowadays when they ask you and they say, do you want all the cookies that are available on this web page? Some of those cookies are used to track you. Right? So you might go through to that list and go, no, I don't want the tracking cookies, right? I just want the ones that make the web page work. Right? So that's why you would do that. However, a lot of people are in a rush and they just go, I don't care. I'm going to just use all the cookies and then just take the consequences, which is fair enough because maybe they're not bad consequences. I mean, you can't tell. But if you do go through and say, delete all the cookies on your browser, which is an option in your histories, you can delete all the cookies, you find that your browser and your web experience is diminished because all of a sudden you find yourself having to re-log in to many places along the way. Anyway, so that's HTTP cookies. Next. I'm going a bit longer because I thought I had a lot of time, so sorry, I'll try to speed things up now. Right. So this is all very interesting, understanding about how networks work, how protocols work. So for engineers, and IT specialists and cybersecurity people, sometimes we have to scrape beneath the surface and try to work out what is going on, right? And sometimes we need to look to see what are those messages called packets that get sent back and forth. Okay, so there are tools that basically capture packets that are sent out on the network. In some high security environments, it's quite common to store every single packet passing over the network for a certain amount of time. And maybe this slide is a little bit old because I think memory is cheap and hard drive space is cheap, or is cheaper than it used to be. So now almost any organization with decent resources can do that. They can store every message that's sent for a certain period of time. Okay, and that period of time might be a day, it might be a week, it might be a month. Well, no, probably it'd be for a day, but at least it would store it, right? Which means that engineers can go back and review it, analyze it, try to work things out. So there's two types of engineers who would go back and look at these. One would be network engineers, and their main task is looking at the packets to make sure you get quality of service, efficient, fast broadband speeds, right? Or network speeds, right? Because they would look at where the efficiencies are. The other person who would look at these packets, security engineers, to see what information was sent across and what information was taken away, right? So having a good understanding of interpreting these packets is important for cybersecurity people, and that's why we've added it into the competition. All right, so there is a trade-off. Capturing all this traffic can be extremely storage intensive because basically it means everything that's been downloaded and uploaded gets stored in addition. So not only the data, in addition, all of the different layering information as well. Okay. So usually there are actually many tools that you can use. TCP dump is a command line tool that's very commonly used for by professional engineers who know how to use it, I suppose. It's a command line tool. But the one that we teach our students, and I would imagine almost like everybody in industry uses, is called Wireshark. So Wireshark is a graphical tool which actually allows you to examine the packets. All right, let's go to the next slide, Ross. All right. So sometimes Wireshark is known as a network sniffer, network analyzer, lots of different things. So you can also see that Wireshark is not alone. There are many other tools that you can use, and certainly if you have access to some of these other ones, and if yourselves or the students are more comfortable with them, then happy for you guys to use them for the competition. But Wireshark is probably the most popular. TCP dump was the original, so usually it's installed in lots of Linux distributions. And T-Shark is probably another command line one that's getting more. It's come from Wireshark. It's the command line version of Wireshark anyway. So there's a few other ones that people might want to use in there as well. And you can see in the screenshot there an example of what Wireshark looks like. The really interesting thing about looking at packets in Wireshark, you start to realize how many packets are actually sent across the network without you realizing. Because, of course you think, well, I hit the go button or hit on my browser, and of course there's going to be something sent out across the network, right? But there are hundreds of packets being generated, sent, and received without you ever having to touch anything at all. Right, so as soon as you plug that cable in or connect to the wireless, this starts happening. Transmission starts happening back and forward between your device and the network, right? And you can see here them all starting to line up there. Let's go to the next slide. I think we have more examples of what Wireshark looks like. I think this one's a little bit out of order. But one of the interesting things that you can find, was it?
I went slightly too far, I think.
Yeah, because I was expecting this slide. So this is Wireshark and basically how it works. And you and the students will be using it for round 2. The important thing to realize is that there are 3 main windows on the interface. The first one is the packet list. So the packet list is all the packets that have been captured. The cool thing about Wireshark is that you can stick it into real-time mode, and it will capture packets in real time and display them for you. And you'll watch them just scroll up off the edge of the screen because they just keep coming in. So yeah, there is a way of doing that, but we won't need you to do that for round 2. We will have created an example of captured packets, and it'll be up to the students to analyze those packets. So in the packet list, you'll see each line there is one packet, and you can see the time when it came in, the source and destination, the type of protocol it is, and then a little bit of information about it. That bit of information can be a bit about the data of it or what that particular packet was used for. So then once you highlight one of those packets, you can go to the second window will display the packet details. Now, you'll notice in the second window there's a lot of pluses and minuses on the left-hand side for that packet. On the system, you can hit plus and it expands out that packet. Each one of those pluses and minuses actually represents the layers that I was talking about before, right? So, yes, I wasn't just talking about it for nothing. The layers are actually there in real life, right? So you can look at each of those different layers to extract the different information out of them. And you can see here, there's a thing that says Ethernet 2, maybe the second line in that window, Ethernet 2. And you can, if you scroll along, and you can see that the number in the brackets, that is actually a MAC address. So it's the data link layer address. Right? And then if you go to the next layer down, the next one row down, and it says Internet Protocol, that's at the network layer that I was telling you about before. And if you go across, you can see there's a source and a destination. And if you guys have seen IP addresses before, you can see a source IP address and a destination IP address. Right? Then the next layer down is your transport layer. Remember, there's 2 different types of transport layer protocols, a UDP or a TCP. And in this example, it's UDP. But you can see, remember, the addressing at this layer is port numbers. So you can see there's a source port and a destination port. And that port number actually identifies the program that should receive this message. Right? But then the other interesting thing is that if you wanted to get into even more detail, you can go to the third packet a third window down there, which is the packet bytes. So there's a packet bytes represented in hexadecimal. So you can start diving really deep. Now, we don't expect you to get to the third window, right? And I don't even expect first and second years to get there. Third years, maybe we'll go down there. But yeah, you probably don't need to have to look at the binary down there. But if you've been playing around with some of the cryptography exercises, you would have been playing with binary things down there as well. And in actual fact, in networking, cryptography is integral, right? Because nowadays, when we send data across networks, they're not in the clear; they're always encrypted, right? So yeah. But anyway, one of the things with this packet analysis is that there's an opportunity then to look at the actual data that's being transmitted across. And then you can click the data thing here. And this example here, the application protocol is a simple network management protocol, SNMP. So if you click that, you could actually see some of the details for that particular protocol. All right, let's go to the next slide. So some of the interesting things that you can find in network captures is authentication. So in the old days, whenever we were sending protocols, sending data back and forward, well, one of the pieces of data that we do send back and forward, usernames and passwords get sent across. So username and passwords do get captured by network captures and things, and can be analyzed and can be identified. And then so if you're trying to break into something, if you could do a network capture and you could see someone logging in, possibly see the transmission of that data going across, and then all of a sudden we activate all the things we were talking about in round one in terms of decrypting something. Okay, so yeah, and certainly in particular protocols, they'll have different ways of authenticating. So this example here uses a protocol called FTP, which is File Transfer Protocol. It's used for transmitting large files, not necessarily large. When I say large, it could be any file size, but for transmitting files. And this particular protocol has a sequence of messages that can be used for authentication. HTTP has a sequence of messages that can be used for authentication as well. So yeah, it does mean some of the older protocols, such as FTP, such as Telnet, were not designed with security in mind. And so sometimes, shockingly, the passwords are sent across in the clear. And so, yeah, you could probably capture those things. All right, next. All right, so this is just looking at different protocol layers. So now we're down at the IP layer, and I guess this layer is kind of familiar in terms of we know about the IP addresses, and you can see the IP addresses in the header there. But then you can split it up, and you can look at all the other things that happen at this layer, which you don't need to know, and the students don't need to know really, but you can just appreciate the detail of data that gets sent back and forward with every message that you get sent. You can see all these different flags, all this different information about the packets that get sent. All right, next slide. Yep, so we're going through the different layers now. So the previous one was the network layer. Now we're at the transport layer, and you can see at the transport layer, it's got your source and destination ports. But again, it's got a whole other set of header information, flags, other kinds of things that get sent back and forth there. All right, next one. So at the transport layer, I did tell you that there are two different types of protocols. One's a TCP protocol, one's a UDP protocol. So one of the things about the TCP protocol is that it has a setup and a teardown. So to set it up, it needs 3 messages that be sent back and forth, and that's why it's quite often called the TCP three-way handshake, or even just the three-way handshake, where a sequence of messages get sent back and forward between the two ends to establish a connection. Right? Once that connection is established, any messages that get sent back and forward are kind of like part of that same connection or session. All right. This doesn't happen with UDP. So remember, with UDP, it's just like a single message that just gets sent, and then a single message gets received, and then we just keep going, right? But the reason why we have the connection in TCP is that once we have the connection, we can start sending semaphore information between the two ends, right? So there's additional information that goes, all right, I sent all this information to you. Did you get it? And then another acknowledgement comes back and goes, yes, I got all those messages. Or the acknowledgement comes back and goes, I didn't get them. And so then what happens with TCP is a really complicated but really cool way of actually going, oh, we're missing this packet. It got lost a long way. Let's resend that packet, right? And so that's the thing with TCP, is that it ensures that that no data gets lost. Even if it does get lost, it resends it, right? And it has a little joined together. Like it's weird. It's a big puzzle at the other end, because each of the packets, each in a larger message, is a number. And then so at the other end, the person's collecting all the different numbers and going, all right, we get them all in order. Let's reconstruct this thing and send it up to the next layer, right? So at the TCP layer, there's actually a state machine, really complicated state machine, that not only ensures that data is not lost, but it also ensures flow control. So it'll send a message back to the other end saying, hang on, I realize that we're losing heaps of packets. Start sending them slower, right? And then so messages come slower. Or it sends a thing that says, have you got more stuff? I'm ready. You can keep, and then you can actually, it can actually control the flow of packets getting sent back and forward as well as the efficiency of it. And it all happens underneath the hood, and you don't realize. So, yeah, the TCP protocol is actually pretty cool. And
while we're on that, actually, I've got a good question from Naomi.
Oh, yeah,
is Wireshark using layers from the TCP/IP model or the OSI model?
Yes, the TCP/IP model is the one that it uses. It doesn't necessarily hold the other information, that the session and the presentation layers. And you can see inside there, it just goes from application to transport network data. So yeah, that's just the way it is. All right, so inside Wireshark, there's a whole bunch of other things that your students and yourselves can explore. A really interesting column is the statistics menu. So inside the statistics menu, you can look at the general overview of all the packets that were captured, a general flow, looking at all the different sources and destinations, to get an idea of what it is that's happening, right? And so certainly this will be probably part of the questions that you get asked as part of the competition, to actually just kind of examine the evidence for the network analysis. So looking in statistics is an interesting place to start. So flow graph is one of them. Next. One of the other interesting things that you can do is, I talked about TCP before, right? So Wireshark understands that all these packets can belong to a particular session. But the trick with all these packets is that they're usually interleaved with all these other packets that are coming around. So you can't expect that a whole bunch of TCP packets all belong to the same session. There might be multiple sessions happening, because, I mean, I've seen my kids and them using a web browser, and I can't even count the number of tabs across the top because there's so many of them, right? But each one of these tabs has got multiple ones of these sessions going on at the same time. So how can you possibly work out which one is which? Well, the system actually does know that, right? So it's got little tags and labels and stuff like that. So what Wireshark can do is that if you select a particular TCP packet, you can right-click on it and say, I want to follow the TCP stream, and it will open up another window, as you can see down there, and it actually collects all the data in that stream. So you can see here, if you got good eyes and squint, that it's actually trying to follow the stream for a HTTP packet, right? And as we know, HTTP packets have two types of messages. One's a request and one's a response. And you can see the first part is the request. It's requesting something, and that's in red. And I don't know how it chooses the color. It's just one is red, one's blue. And yeah, anyway, the other one that comes back is blue. All right, and it might randomly choose red or blue, but I mean, it just separates out the direction that they're coming through. So theoretically, you can see the conversations happening in TCP. Right, you can't do this for UDP because UDP doesn't set up a particular session. Right, it's just single lines off, but TCP doesn't. It's got that in there. So this is one of the big hints for the competition as well, is to try to identify interesting conversations that are happening, and they're all interleaved between each other. So there are interesting things that you can do beyond what we expect in this class. Things like extracting out data from these packets, reconstructing whatever has been sent and received as well. Because if you're capturing everything that's sent, you can do exactly what the original endpoint would do if there's a giant picture that's being sent across and it's been split up, because one of the things is packet sizes have a fixed length, right? And usually if you're going to send a really beautiful big picture, it's not all going to fit in one packet, so it all gets cut up into smaller pieces and then reconstructed at the other end. But you've got enough in the capture to reconstruct it yourself. And part of it is looking at these streams, cutting and pasting the bits out and joining them together. But you don't have to do that. I don't expect students to do that, but there is potential there. And certainly if you do the digital forensics class, that's what we do. All right, next slide. All right, now as you can see, there's a whole bunch of packets, like tens of thousands. It's going to be like, if you're going to look at every single one, it's kind of like you need to get a life. So, so how do we narrow that down, right? One of the ways is streams, right? So you can narrow it down to that stream. There's a particular menu bar that's really important for Wireshark, and that's the one underneath the icons there with the red rectangle, and that's the filtering menu, right? Inside the filtering menu, it's got its own little language for kind of like saying, if this field is equal to this value, just show that, right? So each of the streams inside a capture will have a different number, and so inside here we can say, let's just identify the packets with this stream, and it filters it down to just that. Okay, and then down the bottom, it's got the statistics of what it's showing. So you can see here, we're displaying so many thousand packets or whatever. So even with the filter, don't assume that it's going to come down to just 1 or 2 packets. It's kind of like it's narrowing it down from hundreds of thousands to just 1,000. So but even then, it's better than nothing. All right, next to the next slide, please. All right, so if you wanted to do more advanced types of filters, you don't have to learn the syntax for that. There's a helper there as well. You hit expression and you can identify different fields and say equal to a particular value, and it's all just click and whatever, and then it shows up. If you make a mistake in the filtering syntax, it'll have a red background. If it works, it's got a green background like you saw in the previous slide. One of the really important things to realize though is the button next to expression, it says clear, right? And so, because sometimes what happens is people forget to clear the filter. And so they think they're seeing the whole capture, but they're actually looking at whatever they'd previously filtered, right? Because sometimes you might kind of like be searching for something and then, not find it. So there is another way of actually searching for specific packets. If you're looking for a particular string and a particular packet, if you go to edit, find, and unfortunately I don't think I have a slide for this, but it's like edit, find, and then inside there a find thing comes up, and basically it says which window do you want to search in, and there's a pull down menu, whether you're going to search in the packet list or in the I forget what the name of the second window, or the third window, which is all the ones and zeros and data and stuff. So most of the time, whenever I search for stuff, I'm searching for something in the header, and so that'll be the second window one. And It's there. But sometimes if I'm looking for the data, then I'll go into the bytes and search for a string there. And then it will identify. So it doesn't filter. The find doesn't filter. It will just move the highlighted cursor, highlighted packet to whichever one meets that particular search engine. Whereas filters, on the other hand, just hides everything else except what you filtered for, if that makes sense. Right, we're getting to the end. Come on, next slide. More statistics. So again, this is kind of important to get the lay of the land, seeing how many packets there are. And this is typical in terms of like they're all TCP/IP packets. And usually it's split between UDP and TCP. So user datagram protocol is UDP and transmission control protocol is TCP. But most of the time, everything's a TCP. So you can see here there's 86% TCP. And you can have a look at some of the different types of messages that have been sent back and forward, try to narrow down something that you're specifically looking for. Next slide. Okay, so along with statistics, you can actually look for conversations. So we did talk about the streams, but the stream actually looks at a specific one. And like I said, there might be hundreds of different streams. So, just clicking through all of them is not going to be sufficient. So here, the conversation dialog box inside the statistics menu will give you an overview. So at least you know how many of them there are, and then which is the source and destination of those conversations that are going back and forth, so you can actually try to narrow them down and have a look. All right, next slide. Yeah, so the IO graph actually just gives an indication of over a time period. You can see if a lot of things happen at particular times. This is important if you're looking for, say, denial of service type attacks or something like that, where someone's trying to do a brute force. You see a spike, and then you know, oh, I need to go at this particular timing to have a look at seeing what they were doing at that particular time, or not. Or maybe there was just a big rush on, I don't know, Black Friday sales or something. And then there was a big spike then. It could be anything, but you'd have to investigate. Yeah. Next slide. All right, so that's just an overview of Wireshark and networks. And basically, what we're going to get the students to do is just have a look and see what's happening inside a network capture, and there'll be some interesting things inside them that fit within the scenario. Be interested to know if people knew about those things before. I mean, even within the Bachelor of IT, you get to do the basic networking class, but if depending on what you choose, you can avoid the networking stream altogether. So
very, very like it starts getting quite technical in this area. And to your point, I think this is really that data forensic, the start of that data forensic side of things.
Yeah, for sure. I mean, in one of our later classes is the data digital forensics, and network capture is just one of the aspects of that class. So yeah.
And Bill, being in web development kind of area before, like always used to talk about the application layer and the data layer and security within both of those, but I was not aware of the other 5. But they were there, but we never talked about them. We always used to just talk about the application layer and the data layer, and kind of makes sense to your point when you said a lot of the security and a lot of it starts at that application layer, because that's where they used to put the security, was at that application layer or at the server level.
Yeah, and I think I guess Marnie might have touched on a concept called defense in depth. And so it does mean that you could actually provide security at each one of these layers as well. So, at the application layer, you can have your encryption there, but at the I guess the transport layer and other ones, you can put encryption inside those layers as well. And there's different mechanisms for doing that. Whenever you run a virtual private network, the virtual private network injects security at like the networking layer So
it's starting to actually all make sense, this stuff. Just scary. Here we go. Yep, I work with HTTP requests and responses all
Awesome.
the time. Postman, browser, network tab tools, Wireshark, Excel. Always happy to hear another academic's explanation. That's Pete. Awesome. Well done. Does anyone have
hopefully I explained it okay.
Awesome. Does anyone have questions in regards to this or round one or anything in regards to those? I'll give you a sec anyway. I'll touch on kind of next steps on round two. So again, as I said at the start, we'll launch the LMS, so all the theory and, you know, the questions and stuff in the morning, and then you'll have access by the afternoon to the VM. So that gives students a bit of time to get their head around it and put a plan in place. Ernest, are you able to talk a little bit about what students will see and kind of how that VM will look when they open it?
Yeah, so I mean, we're still going to, for a little while anyway, until we run out of resources, make the round one virtual machine available. So when they log into the labs.azure.com, instead of seeing just one box that's labeled ASCO round one, you'll see a second box which says ASCO round two, and then so there'll be a second virtual machine in which they connect to for that one. And then inside there on the desktop, they'll have some of the files, the PCAP file, some authentication log files, and other information. And I think there'll be a description in the set of questions as well that will prompt the students as to what direction they need to go on to find the challenges. And then, of course, the questions will also prompt for things that they need to find within the logs and within the network captures as well. So basically, the questions will look to see what they should find within that, if that makes sense. Yeah. So yeah.
And as far as technical considerations, so if in sense with what we went through with round one, if schools have opened that port range that we sent through, there shouldn't be any issues or there should not be any technical requirements. If Ernest, you mentioned some today that if schools open really specific links for those students and their exact port number, then we may need to open the port range. But if you did that the first time, you should be okay.
Yeah, and I don't think many schools would have identified the specific IP, like the specific link to that specific host. If they just open the range, then that should be fine. It's the same range for the students to connect to, and certainly to get to the lab services portal. That's the same, the same kind of one that they were able to log in to previously.
Yep. Awesome. So no changes in tech, and what we basically any time that during round one we sent out that port range, and we never actually asked anyone to open those specific ports. It's always that port range that we sent out, so they should be fine. But again, if you do find any kind of technical challenges when you open the range, let us know and we'll jump to that. But it should be fine. Awesome. So no more questions have come through. What might have an early mark tonight. Ernest, again, thanks so much for your time. So we've got one more webinar for round two, and that's next week on the 19th. Unfortunately, I'll be in Canberra coming back from an event, so it'll be yourself, Marnie, and Leah. We'll have that one in good hands. So again, let us know.
There's a thing on Monday too, right?
Monday, yes, that is the study webinar. So what we're talking with Griffith and some of our other university sponsors. What we're going to go do in that webinar is really take you through some of the study options around the cyber security that these universities are offering. It gives a chance for students to ask any questions. We actually are really encouraging parents to come along to that one. Like, this is an opportunity for parents and students to meet and talk directly to the universities, ask any questions that they might have, and understand what those, study pathways into cyber look like for their particular students. So definitely come along. We'll send out another email to everyone this week, and should be tomorrow, just with a little bit about this. We should be able to get the recording in and a whole bunch of other stuff. Like I said, round one results, we'll release those early next week. We'll build a leaderboard and we'll send all that out. We'll also look at, as part of that, is providing some of the solutions and potentially a walkthrough on kind of how to solve it as well. So give us a little bit of time for that. We're quite in the depths at the moment. These next few weeks has been crazy. So once we get through round two's launch, we're definitely going to be in a position to have a lot more capacity to do a lot more. But we're just really focusing on this content in the next few days and getting that up and ready. But look, thanks everyone for your support and attending today. Ernest, as always, hit the nail. I learn a lot. Thanks for everyone saying thank you. So I really appreciate that. We'll send out this recording and slides this week at some stage when we get a chance. So please feel free to reach out if you need anything, and thanks for your time.